Yeah, hello and welcome to our next session where Enrico gonna talk about attacks in proof of solvency systems.
Right.
Enrico, stage is yours.
Thank you, Igor, for the introduction. So yeah, as Igor said, like the topic of today is the attacks. So it's like a continuation of the first session. We're still describing like the topic of proof of solvency in general. So we are not yet going inside like the Summa protocol. And also something else that I wanted to say that we discussed with like Y Academy people is, so I really appreciated the fact that the last time you had like a lot of questions. I love that, but that made like we ran out of time, and basically what I'm presenting today was supposed to go in the first session. So to not delay the session, I'm gonna take, I think, 2 or 3 pauses during the presentation to take question, but I will not like take question in real time. So you can still write the question down in the chat, and then I will pause and answer your questions. So the topic, as we said, are the attacks. So now I'm gonna go through a list of attacks. Some of them are like known in academia. Some of them are not published according to my knowledge. And for each attack, we're gonna go through like 3 steps. So first of all, we're gonna describe the attack, like concretely what that is, the risk. So in terms of like the proof of solvency process, what is the risk? Like what is the security risk for the user or for the custodian? And eventually we're going to go through the mitigation of this risk. And yeah, I mean, the mitigation, when there is a mitigation and where I know the mitigation. For some, honestly, we can make hypotheses, but maybe you also have ideas, but it's not 100% clear how to mitigate them. So the first attack is the leakage of users' data. So so like when I say Paul is proof of liabilities, when eventually we're going to see proof of assets, but you see that most of the attacks are related to the proof of liability because like Summa, at least we spend most of the time, if not all the time, working on the liability side. So the leakage of users' data means that like some data about the user and these are also data that are like an important like business data for the custodian are leaked to the public. And this is not a risk for like the, let's say, the soundness of the protocol, but it's more like a risk for the user in losing their data. And the risk, for example, is like, so let's take like the naive approach. It's like doing a proof of liabilities just by publishing the old database. So in that case, it will still be a valid proof of solvency, but all the data are released to the public. The next step is using a Merkle sum tree, as we described in the last session. But if you remember, in that implementation, each user was receiving a Merkle proof, and the Merkle proof was still revealing some data about other users. So me, as a user receiving this Merkle proof, I will see other users' balances. So like one there's a question? Okay. One way to mitigate this attack is to split the balance of each user across many leaves. So this is let's say it's like a patch for like the Merkle sum tree approach. So if each user balance is split across many leaves, then you don't really learn any other user balance. You just learn through the Merkle proof that is given to you that there's another user whose one share of their balance is equal to something. So let's say this is like a patch. The best way, in my opinion, to avoid that, if you're still working with the Merkle sum tree approach, is just by using Merkle zk proofs. So for example, if each user receives a zk proof of inclusion, they don't see any other leaf or middle nodes, and this hides completely other user data from the user who receives the proof of inclusion perspective. So this is the mitigation. The second one is the broken Merkle sum tree. So I won't go too deep into this because this will be the subject of a bounty that we're gonna announce later, but just high-level overview. So if you remember, the Merkle sum tree that I showed you the last time was a bit different. It's just like a subtle difference, but is like the difference was in the hashing of the middle nodes. So if you see now, we're like hashing like 70 left, right. While in the other case, can you guys, like if you're not speaking, can you turn off your microphone? Thank you. So in the previous implementation, the hashing of the middle nodes was like 20 left, 50 right. Like in that case, would have been like 20 left, 50 right. In this case, in the broken Merkle sum tree, we are not like splitting the balance of each user, but we're like just taking as an input of the hasher the sum of the balances of the child nodes. So this basically was like the original Merkle sum tree described by Maxwell, and later someone discovered like a flow into the system, and it was replaced by the Merkle sum tree that I described the last time. So I also referenced like this paper that I think someone also shared in the chat, and I won't go deeper into that again because this is the bounty, but just this is an attack, and if you use this Merkle sum tree, under some assumption, there's some attack that you can make, and I leave it to you to discover how and why. This is another attack that is, I think, the most common and the most easy to understand and to think of. And it's like excluding users from the Merkle sum tree. Also, just another note on that, like I'm always saying like from the Merkle sum tree because we're using Merkle sum tree, and most of the existing implementation use Merkle sum tree, but you can, like, let's say, replace here Merkle sum tree from any generic data structure that is used from proof of solvency. So you see that in the V2, for example, we're no longer using Merkle sum tree, we're using KZG commitments, and in that case, it's still an attack. It would be like excluding user from the KZG commitment. So what happens here? Like the difference in these two Merkle sum tree is on Henry side. So you see here that basically like the Henry's leaf is basically is zero. It goes to zero, and what happens here? Like this is the attack, and the risk here, of course, is that in this in the right implementation, the sum of liability is less. So I mean, here's an error, but this should be 225 ETH. So the risk is that like by excluding user, the custodian commits to understated liabilities. And what is the mitigation to that? So like the simple way to mitigate that, of course, will be for Henry to be verifying their proof. So if this is the committed Merkle sum tree, and Henry, who's a user of the custodian, requests their proof, it will be either not like the custodian won't be able to generate a proof for them, or it will be generate like a proof that doesn't verify. So in that case, Henry could, I don't know, like open a dispute. Technically it's called a dispute, or just like say create some panic on Twitter saying, hey, I wasn't able to receive a proof, or my proof wasn't valid. And this is like let's say the most social based ways to mitigate this risk. There are also other more exotic approach to that. So like for example, like this is just an hypothesis. This is not what Summa is doing. Like, but if the custodian, for example, would like let's say commit publicly like every username and balance, like a blockchain basically, then it would be possible to verify this against the publicly committed balances. But I mean, if we can start thinking about solution, but we have to keep in mind that we are working under some constraints that are like the way custodian operates. So this is a sort of like a thing that I had many times when working with Summa. It's like, yeah, we could think about solutions that are more innovative and that they are like going beyond how a custodian works today. But at the same time, we're offering a product to the custodian. So we cannot go at them and tell, okay, yeah, now destroy your architecture. We tell you how to build your own custodian, and then we're going to mitigate this risk. So this is just to tell you that, like, yeah, we are not able to mitigate this risk in Summa. The only way to mitigate this risk is to create a system that incentivizes user to verify and let user who were excluded to be able to claim it publicly. This is another attack that is basically the same as before. So you can either exclude Henry or understate their balance. And yeah, this will result just in understated liabilities, but it's kind of the same thing. Like if they can either exclude one completely or just reduce their balance, and like the consequence is still the same, that it will result in understated liabilities. So this is another attack, like the balance overflow when computing the sum. This is not an attack, in my opinion, that exists when you're working with like a public tree. So let's say like in a Kraken implementation, well, let's say in the BitMEX implementation, the one that is working with like Merkle sum tree and a split balance, there's no really risk of balance overflow because like all the balances are public, so everyone can check the summation until the top of the tree, and so every overflow of balance will be detected. But when I say balance overflow, I specifically mean overflow inside a prime field. So this is more related when we are dealing with zero knowledge proof and zk snarks. So as you know, I'm gonna explain you like very elementar way. Let's say you have a circuit. You know that like every element, every value that assigned inside the circuit is defined in this prime field, and let's say that the prime field is I don't know, 255. Well, it's not a prime, but let's pick a prime number. If you pick this prime number, let's pretend that like 17, this is our prime field. You know that like every time you perform addition inside this prime field, when you do like, okay, let's say you do 15 plus 1, you get 16. Then if you do 16 plus 1, you get 0. So this is like the overflow that is happening because you kind of perform every operation modulo 17. And this is a risk. Like when we're like doing the summation, this is a big risk. Like if like the 15, the 1, and the 1 are the balances of the users, we don't want the custodian to declare that their sum of liabilities is 0, of course. So we need to avoid that this overflow or like wrapping around the prime happens. And the the mitigation for that is doing range checks. So this is our mitigation. Probably there are like other ways of doing that, but we basically range check every balance that is a part of the proof generation. So let's say we are like summing up 4 balances, and we know that the prime field is 17. In that case, we know what is the prime field. We know the number of summation that we perform. So in that example, if we range check that every balance is at least 4, we know that it will never overflow, because even in the worst case, 4 plus 4 plus 4 plus 4 will be equal to 16, which will not overflow the prime. So if we set range checks, there are basically polynomial constraints inside the circuit, and we are gonna go through that in a later session. We kind of avoid the risk of this balance overflow inside the sum. So I will go one more, then I'll take question. So this is an interesting one, like adding fake users to the Merkle sum tree. So why would you do that? Like let's go back, like it will be, let's say, like from the custodian adding a new user called like Enrico. No, let's say I'm a real, like some fake name that they just made up. And in that case, let's say they add this user with like balance 20. Okay, this is a risk technically, because this will like make a non-valid proof of solvency. Like this user is not part of their user base, so this will generate an invalid proof of solvency. But like, if you think from the incentive point of view, there's no incentive for a custodian to add a user, because this will like overstate their liabilities, and this is something against their interest, because it will basically mean that they need to have more assets to cover these liabilities. So under the assumption that this adding of fake user doesn't cause any balance overflow, then this is actually not an attack. So we can think that this is not an attack. And of course, like the balance overflow attack, like preventing this balance overflow attack requires you to know in advance the dimension of the tree. So you can forecast when an overflow can happen. You basically need to take like two variables into account, like the prime field and the number of summation that you perform, and then you can set the range either like less or more. And there's also another, let's say, more performance-wise analysis here, that you could set like the range check to 128 bits potentially, if you calculate that this won't generate an overflow. But the bigger the range check, the more expensive is the constraint, like the slower will be the proof generation. So in our case, we set the range check to 64 bits, because it's like a good compromise. Like there are no, in our knowledge, cases in which like a balance of a user will be higher than 64 bits. This will prevent overflow, and this will still give us, let's say, a decent performance. Like we could set it higher, but it will just slow down the circuit and doesn't make much difference. Okay, I will take the question now. Okay, can the custodian stake to promise that liabilities are correct? If a user proves they're not included, then stake will get slashed. Yeah, I think so. These are like 2 points here. Yes, they can totally do that, and I think this can be done outside of Summa protocol. But yeah, this is a good idea. But I also agree with that. It's not just like, let's say, if 100 people agree that I was not included correctly, I can I can slash you. And yes, we also thought about using TLS notary for that, but yeah, it gets complicated because every time like attesting a on-chain balance is on-chain balance basically are easy to prove. When you start with like trying to prove off-chain balance is a bit tricky. Like, yeah, TLS notary, if you don't know what that is basically a way to extract attestation from any off-chain data using TLS certificate signatures on TLS certificates. But since the custodian itself is the one who's managing like their server and the data that are served to users, like, I mean, if you open Binance and you see like 0 in your balance today, if you open your profile, like there's really nothing you can do. Like they can change the data that they give you every time. So this is kind of tricky. And like the more you think about this, the more you see that like how like, you know, decentralized application are more sound for like this type of attacks. Can you briefly repeat the mitigation to the third attack, excluding users? What was that? Okay, yeah, I mean, uh, okay, like so this is like it's not really a mitigation. It's basically a way to, let's say, build a different custodian. But like, let's say you're a centralized exchange, okay, and you basically at every time you publish let's say this is the state of the custodian, and you will need to sign every transaction. So as a user you sign a transaction, and you make a transfer, you sign it as a user, and then this signature or your updated balance based on the signature get published somewhere like on a blockchain. Then you know that like your actual balance at this state is equal to 10 because you sign it. So if they exclude you, you can use the signature to prove it against. Or another way could be like just to build creating a zero knowledge proof to build this Merkle tree based on the committed signature, on the last state committed signature. But when you think about that, I don't know if this makes sense, because you know the like users use custodian because they don't want to store keys. So if we insert a key in the system, that will make stuff more sound from a security perspective, but we're like basically creating another problem for the user. So we're like damaging their user experience. I didn't understand how MST can leak data except for the total liability stored in the root. Yeah, this is the correct answer. So if you're not using zero knowledge proof, every time you receive a Merkle proof, let's say you're Alice, you will receive this node, and this node, right? Yeah. So this node will tell you that there's a user next to you. You won't know what is the name of the user because their username is hashed inside the hash. And you can think that you cannot solve here if you want to make like the hash more secure, more difficult to fetch the username, but you can still see that what is the balance of the user. So yeah, basically you can follow the trade of the user next to you progressively according to each Merkle proof that you receive. And this is what we are trying to avoid using the Merkle proof. Well, sorry, the ZK proof. Okay, this is another attack, the collusion with a whale. and exclude them from the Merkle-Sum tree. So this is not like I didn't take this from academia, as you can see from the name we gave to it. But this is like a very social attack that I don't have an answer to that, honestly. But let's say there's like a big whale, like a user with a very, very big stake, like they have big balance inside this custodian. The custodian can go speak with them and say, hey, don't worry, like we're going to exclude you from the liabilities, but if something happens, like if there's a liquidity, like there's like basically if the custodian defaults or they don't have liquidity to pay the deposit, we sign a contract and we ensure that you're gonna get paid. So in that case, the whale won't open any dispute, even if they were excluded from the liability stream. So this is tricky. Dispute resolution. Okay, so we analyze like the attacks and one of the well, like the solution for many of those attacks was basically just allow users to verify their correct inclusion, right? But let's say that you were like Henry here, that was like first excluded, or in the second round, completely like it was like understated their balance. So I'm a user who was like misrepresented in the Merkle-Sum tree, excluded directly, or didn't receive the proof of inclusion, or in the first two cases, I received a proof of inclusion, but this wasn't valid. So it was valid because it verifies according to the commitment, but the balance that was included in this proof as my balance was wrong. So how can I convince the world about this? And this is basically like the question that was asked by, well, like this suggestion from Y5 Yash about like using TLS notary. This can be a solution, but I think a solution to that will be similar also to the one that I said before. So if the users and the custodian are signing each user state, so each state is like double signed, then if my state at T1 was like Henry balance 10, and this state was like signed by the custodian and then signed by me as well, or maybe better the opposite, first signed by me and then signed by the custodian. And at T2, when the proof for the proof of solvency regarding T1 is done, and I receive a proof of inclusion that says that my balance is equal to 5 rather than 10, I can take the sign message that I got before that said my balance equal to 10, and I can convince the world about this. So it's not like a social proof, it's more like a formal cryptography based proof. But again, like yeah, I wish we can do that, but this would require basically to build a new model of custodian. So we don't implement this, and yeah, honestly, we didn't add any interest related to this proposal from like customers. So they don't want to basically give keys to user to sign stuff. So it's a kind of this is a solution that I had in mind, but this is not mitigated yet in our implementation. Shared user ID. Okay, this is interesting. Like in this implementation, we take as a ID the name of the user. So this is supposed to be like the username if the custodian as a username, or can even be like the email address. Okay, and of course, when we're working with like a circuit, like we need to transform this to a big integer. So we do like some parsing to transform this username into a big integer, and this is fine. Like if we use the email or the username, is fine, because if you receive this, you know that it's you. Like you know that like this email is yours, and if someone else received the proof, the same proof, they can tell that this is not their email. But there are occasions, I think Binance has that. Well, many implementation, they don't use usernames. They just use a user ID. So I don't know, you are given a proof that instead of Alice says like some random identifier like 1 2 3 4 5, and you're supposed to believe that this is your identifier. But in the case that there are two different users that have the same balances, so let's say there are like two users that have both 20 ETH and 10 BTC, they can be given the same proof with the same ID, and they cannot tell if this is theirs or someone else. And this will basically result in a understated liabilities, because rather than adding this 20 ETH and 10 BTC for like two leaves, because there are like two users, you can kind of merge them into a single leaf, and using this identifier that is not tied to any personal information, you can trick the system. So this is not a huge attack, because you still need to have users that have exactly the same balance, and if it's multiple currency, it becomes difficult to have the same balance, but still is an attack. Inconsistent root commitment. Okay, this is also interesting. Like as we said like the last time, for like every time you do like a Merkle proof verification, you need to verify it against the root that is committed publicly. But let's say that the root is hosted on the custodian server. They can potentially give a root to you, then they can give another root to someone else. So let's say if the total liabilities of the custodian are like 400, they can split the user base in two groups, and let's say that each of the groups result in a liabilities of 200 instead of 400. Like I can receive the commitment for the first group, I can verify my inclusion, and according to my perspective, the total liability of the custodian is 200. Someone else that belongs to the second group receives a proof of inclusion, verifies against this different commitment, and again, according from their perspective, the liabilities of the custodian is 200. And this can be verified against a total assets of 200. So this is more like a communication problem, I guess. But like if this commitment is not published anywhere that every user can see, then this can be a trick. So if let's say if the custodian publish this root commitment on Twitter, this is a solution, and then every user can see, okay, this is the actual commitment. But if it doesn't get published anywhere, but it's just served to each individual user, then this can be an attack. And what we do to mitigate this, well, I mean, if you see like how Summa works, this root commitment, Merkelson tree root hash commitment and root balance too, is published inside the smart contract. So I think this is the best, of course, for like a consistency of data and like timestamp data, because it's kind of protected by the Ethereum consensus. But I would say that even just publishing something on Twitter or on a blog post on some website is still kind of good enough to prevent this attack. Pattern recognition of lazy user from the custodian. This is also very, very interesting. Like as we said many times, the soundness of a proof of solvency protocol relies in the user performing the verification. So if zero user are performing the verification, then the custodian can claim whatever liabilities they want, and they will never get caught by the public, right? But there's also another risk. Like, let's say that there are like many rounds of proof of solvency. There's like we do it like the custodian performs it like every day, and if the action of like requesting the proof is performed by the user, so if the user needs to go to the custodian website and press a button that is like get proof of inclusion, or even if it's like an email and they need to click a link to fetch this proof of inclusion, the custodian is able to track the name of the users that are requesting the proof and that they are performing the verification. So if this is done many times, they can start seeing some pattern of like what are like the users that are actually performing the verification, and what are the users that are never performing the verification, which are like the lazy ones. And starting from this information, they can say, okay, if this user hasn't verified their proof for like the first 100 rounds, it's very likely that they won't do it for the 101st round. So they can start excluding them from the liabilities tree, and they can kind of, let's say, bet on the fact that if they were lazy before, they were gonna be lazy even after. And the mitigation for this, so there's like some partial mitigation that I think is done by BitMEX. Is the only one that they are really probably concerned about this attack, is that they generate the proof and they make basically a third party be the one that is like distributing this proof to the user. So in that case, it's this third party that knows the user who verify their proof, and it's not Kraken that recognize this user. But this is a partial solution. Like, honestly, I think like the best solution will be something that is called private information retrieval. This is a technique based on fully homomorphic encryption that allows you to fetch data from a database without the database knowing which data you are requiring and therefore who you are. But this is, I mean, of course, not very efficient. And another way will be, like in the case of Summa, for example, the proof itself can be made available to the public because there's no secret information that are, or private information that are revealed with the proof. So we can potentially think about a way of generating these proofs, publishing it to IPFS, and then let user fetch the proof from some IPFS node that we can assume that is not colluding with the custodian and telling them which proof was fetched. So this is a solution, but there's there's an issue here that in case of Summa, the proof of inclusion, I wouldn't say is slow, because it's like generating a proof of inclusion. I think you see that our benchmark are always benchmark against Binance as the biggest user base. It's 2 to the 28 users. So it's like 100, well, like around 200 million users. So it's like a lot, honestly. And the proof of inclusion in that case, it takes us 400 milliseconds to generate. But if you think about generating 200 million proofs that each of them takes like 500 whatever millisecond, it will take like honestly a lot of time and a lot of money, even if you want to parallelize that. So it's difficult for us to do that, because or for anyone really, like to generate all this proof at once and then make it available for the public to fetch, while it's more easier to just generate them asynchronously, well, on demand, generate them on demand when the user wants them. But in that case, we're exposed to this risk of pattern recognition. So, okay, we have just one attack on proof of assets. I will see what you wrote, guys, in the chat. What if the custodian can know if a user verify? Can know if a user verify? If a user like them sending a mandatory email to every user. What if I don't understand, honestly. What if a subset of user proof is made public and the subset is decided only after the root is committed? So maybe like the first question, I guess, is just like sending the proof by email and then let them do whatever they want. I think probably this is, if this is what you mean, this is a potential solution, but I'm not sure how it works. But I believe that there are like some software that allows you to track emails. Like you can track if someone opened an email. I guess that this exists. Like I can, me as a sender, I can track if user like are opening my email or like opening the attachment. But if this is not true, yeah, let me know. Yeah, there are extensions for that. Yeah, we also had another solution that it was like very old. I mean, very old. Like we thought about it like in the early days to mitigate this risk, and I can share this solution to you in the chat. Well, later on Discord. It's just for probably for like your own curiosity, but I wouldn't be able to tell it right now because it was like a long time ago. But it was similar to this idea. So we were basically committing, like the user who wanted to verify the proof would commit this request, and then the custodian would basically be forced to generate and verify the proof for those users who committed. But of course, the custodian didn't know before which are those users. So I will remember to share it in the chat later. And then we go to the whale friend attack. So now we are like moving on the proof of asset side. And so as I think there were like some question in the chat about the proof of assets, like how Summa deals with proof of asset. And the answer that nullity, if I remember correctly, gave was correct. So we're not putting much constraint on the proof of asset. We basically just allow the custodian to send a signature, which is just some bytes, and then they attach like the public key, the name of the chain, something like that. So in this way, we don't really need to you know, there are like many chains, and you don't know like how many chains exist and how many shitcoin are like supported by this blockchain. So I think, yeah, most of them are just like a fork of get, and then it's like the same signature algorithm. But there are also like many different signature algorithms. So the first idea that we had was like, okay, let's create a customized signature verification for each chain. But then it became like overwhelming, honestly. And so we decided, okay, let's just the custodian publish their signature, and then the verification can be performed off chain. So there are like many libraries to verify ACDSA, ADDSA, whatever type of signature, BLS off chain. So in the smart contract, we're not even actually verifying the signature. So this is all happening off chain. But this is not related to the attack. Like the attack is that as a custodian, I can leverage a friend of mine to do this proof of asset. So there would be like two ways of doing that. First one, I can ask this friend of mine just to send me funds. So I will tell them, hey, I need to do the proof of solvency tonight at midnight. Can you send me all your money? I promise that I will give it back to you just 1 minute after. And this is doable, but this is not very clever if we are like working in a domain where like the public keys are public to everyone, and of course the transactions are public to everyone. So this is easy to detect, but this is not always the case. So there's also a paper, and I think this is also what Amit, which is one of your fellow, is working on. There are implementation of a private, like let's say a fully private proof of solvency that is also private on the asset side. So you protect the public key of the custodian, you protect the balance of the custodian itself. So in that case, this attack become more possible, because you don't see the public key, you don't see the transaction. So this is more a concrete attack in that setting. While in the current setting, the most, in my opinion, risky attack is like just someone sharing a signature with you. So in that case, this friend that is the one with a lot of money in their account will just perform a signature. So if the message is like Binance proof of solvency midnight 19 January, they can ask this guy to do this signature and just share it with me, with the custodian, and I will use this signature. And yeah, this can be done potentially, but now if you do that, you're basically like you are dependent on this friend of yours for your proof of solvency. So if this guy, I don't know, they decide to sell everything, then like you're kind of tracked by them in their operations. So it's a possible attack, and we decide to not worry about the proof of asset because it's another big issue. But probably there are more solutions to that. Like, for example, if we ask them to perform the signature at every round, then it will be more difficult for them to coordinate with this friend every hour, if it's every hour. So probably if we increase the frequency that this signature need to be performed, then this attack becomes less likely. Sorry. There's this link, which is an HMD file that I'm gonna share with you later. That is an internal document that we use to collect these attacks, and also is also created by some guy from Coinbase. So it's not only Summa. And then there's also the bounty. Well, I take the question later. Let me explain you the bounty. So I just kind of teased you before about the broken Mercosur tree. So if you see the broken Merkle sum tree, as I said before, for example, in this case, it uses three arguments as the input of the Usher function rather than 4. So in some case, well, in a way, this is a broken tree, but it's more efficient because you reduce like the computation required to perform this hashing is less than the, let's call it like the new fixed Merkle tree. But for some reason, Summa is using this broken Merkle tree. So we started using the safe Merkle tree, but we moved to the broken Merkle tree for efficiency reason, and we believe that under some assumption, it's safe to use the broken Merkle tree. So the bounty is for you to try to understand why a broken, let's say, first of all, you should go and understand why this is broken. So you should read the paper that I'm gonna share and learn why this is broken. Then you should think about like ways in which this can be made safe, and this is why we made it safe. Well, why we believe this is safe. So basically, the subject of the bounty is this, and I believe that right now, like zero x AI created a channel on Discord for the bounty, and yeah, in that channel is gonna be like the challenge is gonna be described a bit more better than I did. So that was the end of my presentation. Next presentation will be about Summa, and I think now we have a few minutes left for any question you guys might have.
Yeah, so Nagu will post details for the bounty in the bounties channel, and please be aware, like if you're posting the answer, maybe use like masked text Discord feature so that other fellows wouldn't see immediately like the answer and would have opportunity to think themselves.
You know, Igor, what is like the deadline for the bounty? Maybe
I don't know. You choose.
I choose. Okay. So I guess that on Monday, I don't know what is the updated calendar, but I guess on Monday there's it's not me, right? There's a nullity session. Correct?
I think we moved nullity session to the other day, so it's your session.
Okay, my session on Monday. So, okay. Are you sure? Because I still see nullity in the calendar.
Yeah, because it wasn't yet updated.
Okay. So then we can probably set it as a deadline on Wednesday. So hopefully you can start thinking about this challenge, this bounty this weekend. Then on Monday we are gonna have an overview of Summa that can also give you more information on that. And on Wednesday, which honestly now I don't know, but there must be another session. So the deadline
Yes.
will be before this session, I guess.
Yeah, so
So
Monday's the deadline, and Monday we do the code base review, right?
no,
Wednesday.
Wednesday, yes. No, on Monday it's not yet code base review. So I will write down in the chat Wednesday before the session. Deadline. I
Sounds
couldn't
great.
find the bounty challenge. Okay, for this information, you know, like Y Academy guys will be able to answer. Not me, honestly.
Yeah, we're gonna open the channel together with the post on the bounty and highlight it in the announcement channel.
Perfect.
Yeah, I think there are no more questions. So we can wrap it up. Thank you, Enrico. Thanks, everyone.
Okay, thank you. Of course, if you have any question, you can share it on the Discord, and I will answer there.
Great. Have a good day, everyone.